Good afternoon, everyone. Welcome to the fourth webinar that is organized and hosted by the Elmarco company in the Czech Republic. This time we will focus on the usage of nanofibers and electrospinning in medical applications. And at first, I have to also invite you for the next webinar, which will be held at the end of March, and which will focus on electrospun membranes for photocatalytic applications. Today it will be a special event because we have two speakers and two topics. The first speaker will be Professor Andrea Ehrmann from the Bielefeld University of Applied Sciences, and her topic will be the growth of mammalian cells on electrospun nanofiber mats. And the second speaker is Henrik Alexander Christ, Master of Science from the Fraunhofer Institute for Wood Research in Braunschweig. And his topic will be, he will talk about electrospinning of modified chitosan for medical uses. Each lecture will last about 30 minutes. And at the end of the overall session, there will be a discussion also that will take also about 30 minutes. And I would like to ask you to send your questions via the Q&A feature of Zoom. Now I would like to ask my colleague Katarina to give a short presentation about the Elmarco company.
Yeah, thank you, Lukáš. And we forgot to introduce you, actually. So it's Lukáš Plištil. He's a chemist working at R&D department already for, I don't know, 15 years. So he's experienced. And so he can ask speakers a lot of questions. So about Elmarco, it's my pleasure again to introduce and to maybe talk about details about the nanospider technology, which is the technology that's been invented, let's say, by Elmarco. Elmarco is a company which is being on the market for more than 20 years. And well, the core business of us that we are selling machines. More details about the structure of our technology is that we are using wires as a spinning electrode, and basically is working like that we are distributing the polymeric solution on the top of the wire, and the spinning is taking place from the surface of the wire by generating the fibers which are coming towards the collecting electrode and the moving substrate. So we always have to spin on moving substrate. Our technology is also called roll-to-roll technology, where we are at the one end have a empty roll of a substrate. On the other end, we are collecting substrate which is being coated with nanofibers. Okay, so now you can also see the technology working on a short video where you can see the generation of the fibers on the surface of the wire electrode. This is a typical portfolio of machines that we are making and bringing to the market, starting from the small scale laboratory equipment and going through the, let's say, pilot scale production tools, and of course ending with the large industrial machinery setup. The important message is that all processes which has been developed are optimized on a small lab scale equipment, can be easy upscaled. So this will encourage you, all researchers, to actually start with our technology so that you can easily go to a real production afterwards. Yeah, this is a brief, let's say, segments of applications that are using nanofibers. Today, we will be focused on medicine. And medicine is very broad, let's say, area that covers wound care, tissue engineering, drug release, surgical drapes, and face masks, and maybe even more that. It's a rapidly growing segment of the market, and that's why we already are here for a second time talking about medicine. Already now I'm coming back to our main speakers of today. And I want to say a little bit more words about them because I know both of them in person. I met them last year during my business trip in Germany. So it's a big pleasure to invite Professor Andrea Ehrmann. She's very active in electrospinning. I mean, the whole school is just covered with posters related to electrospinning application. So I believe that each student that is there is using our equipment, which is really positive. And I really felt the positive attitude while visiting them. So I'm really looking forward to the topic that they're going to present, or she's going to present. Next presenter, very young scientist, chemist, polymer chemist, which is important and very interesting, let's say, background or profession, because that's very needed for in the electrospinning world. And Henrik is very much focused on the, let's say, biopolymers, and mostly his talk will be on the chitosan electrospinning. And he is also finishing his, or still doing his PhD student with Technical University of Braunschweig. So he's still, going on with the research. So I hope also his presentation will be very interesting. So I wish you pleasant listening. So now, please, I give the word to Professor Andrea Ehrmann as the first speaker.
Yeah, thanks a lot for the kind introduction, and thanks for the invitation and the possibility to present our research here. Let's see. Yeah, as you mentioned before, today I would like to talk about a very special idea in electrospinning for medical applications. This is the growth of mammalian cells on electrospun nanofiber mats. I assume most of the listeners here will already know how electrospinning works, and you already presented it a little bit, and so I can do this very briefly. We have also a nanospiral lab in our university, and the main idea is that we have two wires, which you mentioned also before. The lower one, which is coated by a polymer film, which is coming from this carriage here, in which you have a spinning nozzle, and by moving this carriage along this wire, the wire is coated by the polymer solution. This is drawn to the upper wire by a strong electric field. And since here's the blue one here is a substrate on which these very fine nanofibers are then placed. Typical diameters of the nanofibers in our research area are like 100 to maybe let's say around 1,000 nanometers. So of course they can also be much thinner, and they can also get thicker depending on the material. Our machine is, as I mentioned before, a nanospiral lab. And here you can also see it standing in the lab in a very little corner, because we don't have so much space, unfortunately. Normally, we are working with voltages from 25 to 80 kilovolts, depending on what exactly we are spinning. The carriage speed can be applied somewhere between 100 and 250 millimeter per second. Nozzle diameters are usually around 0.6 and 0.9 millimeters. Since we are also working with sometimes with additional nanoparticles inside the solutions, we took one of the nozzles and opened it a little bit more. So now we have also a nozzle with 1.5 millimeters diameter, which sometimes helps, but sometimes also makes things quite complicated for spinning. So it's a really special idea to make these large nozzles. The substrate, the distance between electrode and substrate can be varied between 120 and 240 millimeters. And we are mostly using the 240 millimeters since we, in most cases, this gives the best nanofiber mats, the most homogeneous ones. The relative humidity in the chamber should be below 40%, and this is quite okay for, let's say, gelatin or some other biopolymers. For the pan polyacrylonitrile, which we mostly use and which I will mostly focus on in this talk, we need definitely below 33%. And this is indeed a problem, because as you can see here on the right side on this image, there's nothing like a real air condition, which is available, I know, but we didn't have the space for this. So in the moment, we reach this simply by compressed air, which makes things a little bit complicated, especially if the compressed air is not absolutely cleaned from oil, and which costed us a lot of months, in which we couldn't work last year. So, but now things are working more or less now. Very often we use only a very small carriage with only 5 to 10 milliliters of spinning solution for the tests. There are, of course, larger carriages in which we can fill much more spinning solution, but for most of our tests, the small one is sufficient. What I would like to show you is some ideas about cells, mammalian cells growing on nanofiber mats. And one of the points which are very important for this is a topic of sterilization. If we don't sterilize the nanofiber mats before letting the cells grow on them, they will have severe problems with mold, with other problems, with contaminations of all kind. So if we would like to use these nanofiber mats, especially for cell growth, let's say for wound healing or for tissue engineering or generally for biotechnology, then we have to care about the sterilization process. We use very often elongated cells. This means, for example, neurids or fibroblasts. And these elongated cells very often like growing on also elongated structures like nanofibers. Sterilization is normally done by autoclaving. This means you have a temperature of 121 degrees Celsius usually, and also a little bit higher pressure. But the autoclaving process may damage the polymers depending on which material you use. So on the other hand, something like simply ethanol is not sufficient. And so we tested further techniques to sterilize these nanofiber mats. We made, for example, tests by autoclaving and compared it with high temperature treatment in a broad temperature range between 60 degrees Celsius and 180 degrees Celsius. But we also used ozone and UV sterilization, which are both quite well known for these techniques. So the experiments which I would like to show you firstly are based on CHO DP12 strain. This is Chinese hamster ovary cells. And this is just a typical model cell, which is very often used in biotechnology. And the first nanofiber mats I would like to show you contain pan and gelatin as a biopolymer. These sterilization tests, which you can see here. Here in the first row, you have some nanofiber mats with cells on them, and they were ozone treated. The second row was hot air treated nanofiber mats. And then the next one is UV treated, and the last one is autoclaved. And here you see no fibers. This is simply the wells. This color here is depending on the fluid which is necessary to let the cells grow and grow properly. And after this sterilization process, we could see quite different effects from these different sterilizations. For ozone, for example, you see a nanofiber mat with quite thick fibers, which stem from the gelatin. If you have a mixture of pan and gelatin, then you have very often you have partly fibers which consist partly of pan and partly of gelatin and which are quite well mixed, but sometimes you have also fibers which contain mostly pan and mostly or purely gelatin. And these thick fibers here on top, we tested them, they are really contain mostly gelatin. The same is here visible also for the UV irradiation. So actually the surface was quite similar to the S-spun surface. But as soon as we use hot air or autoclaving, then you can see that the gelatin starts melting and that the whole structure changes quite strongly. It's not longer really a nanofiber mat. The nanofibers are still below. Everything here below, which you can see here still, this is mostly from pan, and the gelatin is more or less molten and is a little bit, running around there on the surface, and so it's not really gelatin nanofibers anymore. So our first assumption was that ozone and UV irradiation would be the best ideas for this treatment, for the sterilization. And so what we did in our tests is we just checked how these cells would look like, and also we counted the cells, which I will show you on the next slides. Actually, most of the sterilization techniques worked more or less in terms of sterilization. Heat treatment at 60 degrees Celsius was not sufficient, but heat treatment at 90 degrees Celsius was fine to avoid contaminations mostly, not absolutely, but mostly. And now let's start with the ozone sterilized substrates, which you can see here. These cells, which are stained with blue dye here, here, for example, on the left image, they look mostly more or less round, and which, at first glances might look quite nice because they are nice round cells, but actually these cells should not be round. They should start spreading. They should spread along these nanofibers. And here's one picture where they do this more or less, but still you can see a lot of round cells. So maybe this is not absolutely ideal as just the first idea from the optical examination of these ozone sterilized substrates. If you compare this ozone sterilization with autoclaving in both these upper images here and with hot air and UV irradiation, then we can see that the autoclaving leads indeed to much more widespread cells, and this is not exactly the case for hot air, but also for UV. Here you can see also some spreading of these cells. So this is also already a hint that ozone may not be the very best idea for sterilization. And this is what you can also see here. We also made, of course, a quantitative comparison. Here, for example, after 4 days of letting the cells grow, we did this on each other day. So there are some more of these results. And we found that ozone leads to the really absolutely lowest results of cells growing per well, and that hot air and autoclaving are actually the best ones. You can see here really large error bars, which is quite a common effect if you are working with anything biological, because you always have quite large deviations. These biological tests are dependent on so many things, depending on where exactly you took the cells from the cell culture, and that's really usual that these error bars are quite large. So nevertheless, we can see that ozone doesn't work, and UV doesn't seem to be very good, and autoclaving and hot air seem to be better, although the substrates didn't look like nanofiber mats anymore. So nevertheless, we went on with testing other polymer blends, and mostly now the sterilization is done just by autoclaving, as it's really the usual, I would say, gold standard in biotechnology. And now we tested the effect of different biopolymer blends. We always used PAN, which is not water soluble, as a main part, and added some maltodextrin and P protein, which is abbreviated as MP. We also added casein and gelatin, and we also added, as another reference, ZNO. ZNO is done because we also did some carbonization and some carbonization tests, and found that after carbonization, the pure PAN nanofiber mats are quite brittle, and PAN nanofiber mats with ZNO are still quite flexible and so. And you will see afterwards some ideas of letting cells grow on carbonized nanofiber mats. And this is the reason why we also use the ZNO, which is not really the best idea actually from the biotechnological part. As I said, we partly stabilized these nanofiber mats thermally and carbonized them, and then they were autoclaved. And here you can see just the nanofiber mats as they are spun with ZNO, with maltodextrin and P protein or MP, and also with casein and gelatin. And the diameter distributions are quite similar in all cases. Here, as an example, the CHO cells, when they are growing on just simple glass cover slips, you can see that they are growing in this elongated way, and that they try to more or less fill the whole area which is available here. trying to grow them on pure polyacrylonitrile, which is just electrospun or also carbonized. You see that the cells don't really look elongated. On the carbonized pan, they look much better, interestingly, which we didn't expect really before. So on pan with Z and O, there's, well, it's simple, there's nothing. There are no cells at all. They didn't grow there, they didn't adhere to these nanofiber mats. So Z and O is apparently counterproductive in this case. Here for the maltodextrin and P protein addition, you can see quite a lot of cells directly after electrospinning, and also when we carbonized the substrate before, you can also see a lot of cells with which are quite elongated here. And we also found some cells on pan with chitosan and gelatin. Here in these images, you don't see very much cells, but afterwards you will see also the quantitative examination. And there we found also indeed some cells. So pan with Z and O is apparently absolutely not suitable. Actually, this one here in terms of the cells per nanofiber mat, and also if we investigated the viability, so this means how many cells survived the test, and as opposed to the dead cells. This already gives here gives the best results, and nevertheless we found much thicker cell agglomerations for pan with maltodextrin and P protein, as you could see on the previous slide. So now we were still not really satisfied with all these results. Actually, we would like to have some more cells, some better growing of the cells, higher adhesion. And so we went on with some surface modifications. And that's something on which we are working now for some time. Here I will firstly show you another cell line. HT1080 is a fibroblastic sarcoma cell. And we also let them grow on simple pan nanofiber mats because we didn't want to mix too many modifications. We just wanted to concentrate on pure pan and just modify the surface. And the sterilization is again done by autoclaving, or we also tried just hydrochloric acid as a method to sterilize these nanofiber mats. And what we did for surface modification is, on the one hand, vacuum ultraviolet irradiation. So this is abbreviated VUV. The wavelength of this ultraviolet or UV irradiation is 172 nanometers. And this is actually meant to increase the surface energy, to increase the polarity. So this means to have a higher wettability. And this is done by creating hydroxyl groups, carbonyl and carboxyl groups. We also tried plasma treatment. We used air or oxygen plasma, and we combined also these treatments and with VUV first and plasma second, or vice versa. And these cells, which you will see afterwards, were stained with hematoxylin and usine dye, and this results normally in blue cell nuclei. I think there's someone speaking besides me. Okay, but now it's again okay. And this results in blue cell nuclei and red mitochondria. So what you can see here in red are the mitochondria. So the cells, just in a simple well, grown after 7 days, look like this. And on a plasma-treated nanofiber mats, after 7 days, the cells look quite similar. You will always see in these microscopic images that the background, of course, is different because the cell, the well is made to allow looking through it with a microscope, while the nanofiber mat, of course, is not completely translucent. So, of course, it's much more complicated to have a look at the cells on these nanofiber mats. So it always looks a little bit different. Nevertheless, the results are quite similar of the cell growth, which you can see here. When we compare the different treatments after, for example, 3 days of cultivation, then you will see that autoclaving is nevertheless just autoclaving here has the lowest results. We just checked here the covered area in percentage. And the highest results are reached with plasma treatment or with VOB, or also with plasma and VOB followed by VOB, and a little bit less by VOB plus plasma. But again, as I mentioned before, you can see these relatively large error bars. So actually the only thing which you can really say is that pure autoclaving is not as good as treatment with plasma or VOB. Nevertheless, it's a good idea to go further in this direction of plasma and VOB treatment. And this is the reason why we did the same experiments or similar experiments with the cell line, which I showed you before, with the CHO cell line. And here we have now a measure of cell concentrations. So you can see here, for example, a different result, that the UV treatment is indeed it gives the lowest number of cells per square centimeter. And the highest ones, the highest cell densities are reached by UV and 3 minutes plasma, or UV and 2 minutes plasma. We also changed the plasma duration here a little bit. And actually always starting with UV, followed by a little bit plasma treatment. This is here the 3 best results apparently. And yeah, by just using HCl or autoclaving for the sterilization, here you have lower results. And for only plasma treatment, which you can see here, these are the 3 middle ones, this is also a little bit lower results. So apparently this combination, starting with UV and then followed by plasma, apparently this supports the cell adhesion. This was indeed a little bit different for the other cell line and for the test I showed you previously. So it looks in the moment as if the best surface treatment by plasma, by UV, and so on will indeed depend on the cell line which you're going to use. We have also done another completely different experiment. And we went on with different material combinations. Before I showed you PAN plus any biopolymer. And now we also had the idea that we could try to combine anything with titanium. Titanium has the advantage, it's biocompatible, it has good mechanical properties. You will know that it's very often used in medicine and also for tissue engineering. So titanium is a good substrate to let also cells grow on it. And of course, we would like to test, or we wanted to test, whether the addition of nanofiber mats, which are directly electrospun on any titanium substrate, will influence the adhesion and also the proliferation of cells, which are grown on this, I would say on this composite material. We use different titania. So the titanium sheets of grade 1 and 2, these are commercial sheets. Grade 1 means we have the lowest rigidity. And we also used 3D printed titanium 64. And here we could vary the porosity. And so we had the idea that higher porosity may support the cell growth on these structures. We used now here another cell line. These are 3T3 cells, which is the Swiss albino mouse embryo cells, and they tend to adhering on the one hand to the extracellular matrix, but they also adhere quite well to the neighboring 3T3 cells. And now, firstly, going on with a short examination of the surfaces. If we have just the pure titanium surface, for example, for grade 1, then this looks like this. And then we just applied electrospinning for, I think this is an image of 5 seconds of electrospinning, which was already sufficient to more or less cover this titanium plate. And so here in the AFM image, atomic force microscopy image, you can see just only the nanofiber mat on top. So we even have to do it a little bit shorter, but it's really complicated to make things quite reliable if you have these short times. So actually the plan was to have the possibility to see through these nanofiber mats and to reach the titanium sheet. But we will go on with shorter times of. Okay, checking the cells on pure titanium, you can see a lot of these, now in this case also red stained cells. And on grade 1, it's a little bit less than on grade 2. And this was already looking quite nicely. And if we have these titanium sheets with par nanofiber mats on them, then you can see that here's really a lot of cells, of 3T3 cells growing on these nanofiber mats. On the grade 1 titanium sheets with par nanofiber mats on them, as well as on the grade 2 nanofiber titanium sheets, again with par nanofiber mats on top of them. And these cells, if you go a little bit nearer, you will also be able to see that the cells spread widely. So this is they have the right form, and apparently they are adhered quite well to the nanofiber mats. If we have only the pure nanofiber mats, we also see quite good adhesion, but interestingly, the adhesion is not as good as if we have titanium below. So maybe this combination of just having a very short spinning process on the titanium really combines the titanium, which is good for the cell proliferation, and of the structure, of the nanostructure prepared by the electrospinning, which is also supportive for this for the cell growth and proliferation. Nevertheless, we found only for the 3D printed Titan 64 with a high porosity, there we found also quantitatively higher amounts of cells growing than on the pure vial grounds. These vials, on which we normally use as references, are also pre-treatment, which are and they are quite a good method to let cells grow on them. So they have been developed for a long time. The reason why we are nevertheless trying to use nanofiber mats for cell growth is that with nanofiber mats we have the possibility to go into 3 dimensions. And for example, we are also doing 3D printing, and we could not only use a titanium sheet, but also something 3D printed and let cells grow on these sheets after electrospinning on them in 3 dimensions. So I would like to come to the conclusion and the outlook. I would say that from our experiments from the last years, we can conclude that the nanofiber mats, which contain some biopolymers, not all, but many of these biopolymers, are really ideally suited for cell growth and thus also for tissue engineering. We saw that a combination of plasma and VOV treatment can, in many cases, improve the cell adhesion and the cell proliferation. And I would also say that the nanofiber mats can thus be used for tissue engineering. And of course, also just talked today about tissue engineering, but we are also using them for many other possibilities, for many other research ideas in the range of healthcare, of biomedicine, of biotechnology, and so on. Yeah, and with this, I would like to thank you for your attention.
Thank you very much, Professor Ehrmann. And we will continue with the next presentation. I need to mention that all questions will be answered after the presentation, so please keep on writing in the QA feature of Zoom. And right now we will have the presentation of Henrik Alexander Christ on the chitosan nanofibers. So please, Henrik, you can start.
Yeah, thank you for the kind introduction. I would like to talk a bit about electrospinning of modified chitosan for medical uses, and also I've tested some other uses. And yeah, so you see yourself here. Yeah. Yeah. So as you said already, I'm a polymer chemist by training. Most of my time I spent at the Technical University of Braunschweig, and I'm on the verge of finishing my PhD. It's bound to happen this year. I got a bit delayed, but nevertheless. But since 2020, I'm also working as a project leader for binders in the Department of Binders and Coatings at the Fraunhofer WKI. And here I'm working in the lab of Frauke Bunzel, who's listening today as well, I checked. And our broad focus is are wood and lignocellulosic materials. And in our department, we are focusing on sustainable binders and coatings for wood-related products, but we're also doing other various other topics, for example, 3D printing, or standard 2D printing, flame retardant materials, and also we would like to enter the field of electrospinning as well. But as you already mentioned, most of the work I'm going to talk about was done in my PhD group. That's the lab of Professor Henning Menzel at the TU Braunschweig. And his broad focus is macromolecular chemistry. And more or less, he's focusing on medicinal use of macromolecules for implant coatings in the form of nanofibers. We've done a project. He's done a project on bone tendon transition implants made from nanofibers in the beginning, and drug delivery is also one of his focus areas. Yeah, so let's start. To start, I brought you a nice picture of two of the electrospun and cross-linked chitosan samples. That is what I'm going to talk about. And they are sitting, probably still sitting there in water and don't dissolve. That was one of the early problems of chitosan electrospinning, and still is in some cases. And I've tackled it with modification of chitosan. And as you can see here already, the left one is loaded with fluorescent, so it fluoresces under UV light, and you could also show, but I'm not showing this today, that it can be used as a drug delivery system. So we are in the cross section of chitosan, a polycationic biopolymer, in the form of nanofibers with high surface to volume ratios, very good porosities, and also from nanomaterials perspective, also a good macroscopic handleability comparison to nanoparticles, for example. And then the third aspect of my PhD topic and of the topic that I'm going to present today is enzymes and how to fix enzymes on electrospun chitosan nanofibers. Because in the focus area, there are some very interesting medicinal use cases that could be foreseen. Potential medical uses that I can foresee for these kind of fibers are, as I said, drug delivery systems, or also active wound dressings. You can always have to not only imagine the beneficial properties of chitosan and nanofibers, but also imagine what kind of reactions the enzymes that are mildly immobilized on the fibers would also add to the product. For example, some properties such as antibacterial reactions. Also, you could see implant coatings or even bioactive implants that do some reactions in the body that is medicinally good for the patient. Other potential applications I could foresee are a biocatalyst support matrix for heterogeneous biocatalysis, or a protein purification column, or also biosensor applications. So a few words to chitosan. I don't know how many of you listening are familiar with chitosan. It's my favorite polymer, one could say, because it comes from nature, and especially it comes from fungi as well. Another research interest of myself. And there are rough estimates state that there are roughly 10 billion tons of chitosan in the form of chitin, always present in our biosphere. And you can find it in the exoskeletons of insects, crustacea, but also in the cell walls of many, if not all, fungi. And it has many beneficial properties. It is antibacterial and in some cases fungistatic. And it's also very hydrophilic. And the fiber meshes chitosan, of crossing chitosan in water, they behave quite interesting because it interacts very nicely with water. And the main reason why it does this is it's a polycationic polymer, because if you look at the chemical structure, then the primary amine here is able to be protonated in a slightly acidic media, and then it can be dissolved and in water. Because if it would not be would not have this primary amine, so chitin is actually only the M unit, the acetylated unit. So chitin is not soluble in almost no solvent. Yeah, and the main method still for production of chitosan are shrimp shells that come as a waste stream, but I'm more interested in a fungal chitosan. It can be grown in large tank. This is one aspect, but also it comes from a truly renewable vegan non-animal source. In my case, it's actually food wastes from Agaricus bisporus, so the typical champignon. But it also wastes from biotechnology or food industries can be used. And it has been proven that you need less energy and chemicals for its production. And it also has less impurities and especially less allergenic potential than shrimp chitosan. And to get a good standpoint, I'm also hearing you from Elmarco, by the way. To get a good standpoint, we of course analyze the pure starting material. It is a relatively short polymer chain, and very good for us. It is only 10% of its groups are in the M form, so only 10% are acetylated. So 90% of the amines are free to play. As a chemist, I would always like to add functionalities and change structures, and that was very easy to do on this kind of specific chitosan. Maybe a short word to the chitosan I'm using. It comes from the Belgian company Chitosan, which I can really recommend. They're very friendly people over there, and they provided the chitosan for my PhD topic. And it also has very good spinability from aqueous solvent systems, and why this is the case we will explore in the next slides. But before we do this, I would like to give you a short chemistry overview what I've done to the chitosan before spinning. So one main topic was the modification of chitosan, and here I focused a lot on making this modification method very efficient. So it's an amide coupling. You need coupling mediators, EDC and HOP. You see them below. Don't force me to spell them out, please. And we can couple very efficiently with very high coupling efficiency, nearly maximal coupling efficiency, a very high amount of these functional units into the side chains of chitosan. And we confirmed this, of course, with different chemical methods. And beside this, let's call them for now purple and green group, we've tested many different other functionalities, and a lot of very interesting research is possible with this platform. And the purple group we call 4-azidobenzoic acid, is the substance, but we call it aryl azide chitosan. And the other one is biotin, that should be known to most of us. It's natural vitamin, and it is used later on for affinity immobilization of enzymes, but we see this later on. So enough of chemistry for now, because we're talking about electrospinning today. We were not, when I started my research, I did not have the chance to work on a needleless machine. It was not everywhere in the world already, and especially not in our university. So I had to build my own machine, like many other electrospinners. So it's a self-made single needle laboratory setup that we used. It was a cost-effective benchtop solution, and because we've built it from scratch, with the help of a working group in the University of Gießen, we had a very versatile setup. We could change everything and actually, for example, work with a positive and a negative voltage generator. And we added an environmental control unit to make sure that we had reproducible conditions in a nice temperature and humidity range. And also nice was that we could just use, like, for example, a nitrogen and don't worry about explosions. Like one of the earlier sessions, we already talked about this. But for the case of chitosan, we will see that we spawn mostly from water. And another feature that I've added later on in the PhD was to include a strong UV source from above, and that enabled cross-linking during spinning on the fly. So while the fibers are still in the air, or also on the collector. We see a picture on the top right corner. And so if you want to electrospin chitosan or a modified chitosan, it's better to start slow and first get the baseline ready to spin with unmodified fungal chitosan. If you look in literature, electrospinning of chitosan in general is not considered trivial because of various different problems. It starts again with the low solubility of chitosan in organic solvents. So there are approaches that use concentrated acetic acid or trifluoroacetic acid, and I've tried it in the beginning in my master thesis, but I was not convinced because first of all, they stank, and then you had this acetic acid everywhere. And the best approach I could come across was from a researcher, Professor Zhang. I cannot really pronounce his name correctly. In a very nice paper from 2008 that I've read multiple times now. And he proposed the use of a very high molecular weight polyethylene oxide for enhanced spinability. And with that, spinning from 3% acetic acid in a DMSO mixture was possible. And when we tested this using our fungal chitosan, we could show that that it was very easily transferable with very little parameter adaptions. And we could show, I've brought you some pictures that I've come to recognize as a good spinning process. For me, if the full collector surface of 17 centimeters were fully covered, with long and uniform fibers without beads and without any droplet craters. That is a good electrospinning process from my perspective. And the standard fiber diameter that I achieved was like roughly 300 nanometers with a good distribution. So that is the basis on which I set out to explore the world of modified fungal chitosan. And here things got a bit more messy. Basically, different, as I call them now, jet regimes were starting to happen. You have to imagine in the beginning, you modify a gram of chitosan and then you can spin how many hours? Not so many, actually, until you have to create your batch again, and maybe there is some slight differences in how much functional groups you've modified into the chitosan, and that changed electrospinning process completely. So in the beginning, it felt like a jungle of never-ending entangled parameters, and only over time I could disentangle this jungle a bit. And what I found is what I would like to show you now. So I've observed over the times of my PhD 4 different regimes. I call them the electrospray-like regime, the partly chaotic regime, the fully chaotic regime, and a very curious regime, the stable linear jet regime. And they are characterized, first of all, the representations of the jet the observations were made by eye. We did not have any high-speed cameras. So they are schematic representations of what we saw. But what we can really see via photograph is that the coverage of the collector surface varies a lot. And also by SEM images that the beads in the fibers, that there are beads in the fibers and that they get less and less until you only have long and uniform fibers, and then out of a sudden you have thick microfibers that are partly coalesced. So that was the picture that happened in the beginning randomly, but later on when we made rows of experiments and varied only one parameter while keeping all the other parameters in the environment the same, we found that there is some order to this chaos. And there are some critical parameters that we could identify. That is the degree of acetylation, the degree of substitution of chitosan. Also, the molecular weight plays a role. The ratio of PEO to chitosan. Of course, one very important parameter is the concentration of the overall of all polymers in solution, and also the solvent system. So what I did not mention is we changed the solvent, the additional solvent beside acetic acid from DMSO, like in the literature, to methanol, which helped the process a bit. And depending on how much methanol is again giving you it's also a critical parameter. So in general, for example, if you talk about concentration, if you increase the concentrations, then we can see these 4 regimes in that order that I showed it here. That means in that really helps this kind of roadmap helps to see where you are on the spectrum and where you need to go if you want to arrive at the ideal FC fully chaotic process for generating long and uniform fibers. For example, for the concentration, I really made an effort and looked also at the viscosity and correlated the viscosity at 100 reciproc centimeters to the jet regimes and all the other factors, and we could identify a viscosity region in which we could spin long and uniform fibers. And here you can see, for example, if you compare unmodified fungal chitosan, you can spin it from 40 milligrams per milliliter. But if you spin 40 milligrams per milliliter with a chitosan that had 22% of aryl azide groups and 5% of biotin, that was not spinnable into a long and uniform nanofibers, but there we had the occurrence of the mysterious stable linear jet. And with this roadmap, it's doable to generate ideal, perfect nanofibers also from modified chitosan. Of course, as a scientist, you always wonder if you see something and you don't understand it, what happens here? And also it is a process instability in my eyes. So the stable jetting is, from my perspective, a phenomenon that is not yet fully explainable or explained. I've tried to, I would like to try to walk with you to the point where I don't yet find where I'm stuck at the moment. And to prepare this, there is a high-speed video from YouTube. You can follow also the link later on if you want. And keep in mind, here's the needle and the Taylor cone, and we have the jet in a first initial straight section, and then bending happens. And what we see here is only 40 milliseconds. So you all know that the jetting in electrospinning, that there's quite quick. But that is like a typical electrospinning jet. And if we try to figure out, for example, Rennecker has done a very beautiful work on this. If we try to understand why stable linear jetting is happening, we need to understand when bending happens. So when the straight jet switches to the chaotic whipping phenomenon. And I've tried, this is here a schematic representation. So here we have time, and we see the needle and the jet, and we follow the, for example, the first segment of the jet, and we have some charges in the jet, and we have the sum of forces that draw on the jet, and the sum of the forces are is basically an addition, can be, for example, calculated via the drawing forces versus the retracting forces, and the drawing forces would be the electrical field and the charge repulsion, and the retracting forces, they stem mostly from the polymers, from the polymer network, and they are connected via chain entanglement of the polymers. So that's an important thing to keep in mind. And the longer the jet flies, the slower, the more the charge are distributed, and the lower the blue arrow becomes. But the orange arrow, the retracting forces, they increase because they lag a bit behind. They are only acting in effect of the blue force. And so at some point, we don't have any more additional acceleration, if you so want. And only at that point, when basically we don't draw anymore on the jet, that is when the tiny XY bending instabilities really play an effect, and when bending happens. And if we now go back to our 4 regimes, that can explain why this straight section here decreases when the concentrations, for example, is increased, and that can also explain why the collector is covered more broadly, because bending happens more earlier. But what I cannot figure out yet, maybe someone can help me, is why the stable linear jet really occurs. Because if we would say, okay, the bending onset point moves more and more back to the needle, and I would say at the point where the onset of the bending goes inside the needle, hypothetically, that is where linear jetting happens. And that is a bit different from the stable linear jetting electrospinning that is described in literature, where you only move your collector below that point of onset bending, below that onset point of bending, and just put your collector here, and then have the linear fibers. So yeah, there you have it. That's at the moment the point where I'm stuck. But we can still, that did not hinder me to use this phenomenon for some other applications that I would like to briefly mention. So we've used the stable linear jetting to create a highly parallel and highly aligned microfibers from PMMA, doped with laser dyes, and with the aim of checking if this could be a new fiber laser source. That is a different topic that I can maybe touch on another time, but I just did not want to let it slip away unnoticed. But it's actually connected to the other research because of the linear jetting. So let's come back to our chitosan nanofibers. I said in the beginning that that chitosan nanofibers suffer from water solubility, and in fact, if you add water, only a brief amount of time, water to the electrospun fibers, you can see that the complete structure is lost. However, by irradiation, the aryl azide modified chitosan fibers with UV light, sometimes even 10 seconds are enough. We can come over a partly coalesced, partly water instable fibers to fully water stable fibers on the right side. And we can also follow this process via the disappearance of the azide signal. I would like to spare you the chemistry, but basically what happens, the UV light kicks out nitrogen and leaves the N3 group, the azide group, as a nitrene, and that is so highly reactive that it inserts itself in NH or CH bonds of neighboring polymer chains, and then all the polymer chains are cross-linked. And the pictures E and F here below are look the same like picture D. Picture D is from incubation in water, and the others are from hydrochloric acid, quite strong, and also sodium hydroxide. The last slide of results from my side is what I'm going to do. I cannot say so much, but I'm currently finishing this fourth paper on this topic. It's about testing the green group, which I presented in the beginning. Basically, the biotin is used as an affinity tag that binds that can be used to bind proteins like streptactin or avidin very strongly, and to break this enzymatic or proteinaceous bond is roughly the energy you need, roughly the energy as you need for breaking a covalent bond, but it's a more biological bond. And if you fix streptactin on the chitosan fibers, you can then fix other similarly tagged proteins, for example, eugenol oxidase, in my case, to the streptactin, and then bind very different enzymes very specifically, but very mildly, to the nanofibers, and really add a plethora of functionalities onto the fibers. In the case of Eugo, I've just used it for establishing the concept, and because it's a very nice enzyme that also a chemist can work with, and it catalyzes, beside others, the reaction from vanillyl alcohol to vanillin. And the good thing is vanillin is yellow, so it absorbs, it has a maximum in the UV-Vis spectra at 340 nanometers, and so you can easily detect this chromogenic product and differentiate it from the substrate. And so we can do this. We have done immobilized the enzymes on the fibers and put a very small piece of 1 or 2 square centimeters in the syringe filter here, and then push the vanillyl alcohol substrate solutions through these filters continuously into a cuvette, and then we can measure directly the output of vanillin. And after a buffer phase without the substrate and a mixing phase, we can see that we have a continuous output of vanillin, and that the enzyme survived the immobilization, and it is also there, and that you can actually maybe use it for different applications. And we have also done some kinetics, but I will not focus on that topic so much. Yeah, in summary, I presented you an effective and scalable synthesis route for the incorporations of various functional groups in chitosan. I talked to you about the electrospinning of these modified and also unmodified fungal chitosan into nanofibers. I've touched a bit about the parameters that led to the stable jet and how I try to disentangle them. And I also talked about a bit the water stability of the resulting fiber meshes, and showed you in the beginning that also the fibers can also be loaded with small molecules, for example, for medicinal application as a drug delivery system. And in the end, the finished nanofibers are suitable for immobilization of at least eugenol oxidase, but probably for many other functional biomolecules as well, and that hopefully will have an impact in medical applications as well. Yeah, time to thank. I'd like to thank Professor Henning Menzel and all the members and the former members of his working group for the general help and support. Also the group of Professor Annette Schalmey in Braunschweig for the support with the enzymes in the biotechnology. I would like to specifically also thank all of my research interns who did a lot of the work. Some are also listening. And also the Akas Marsli for initial help and support with the electrospinning environmental control setup, and of course the company Chitosan for provision of the fungal chitosan. And of course, Elmarco and you as a listener for your time and your attention. And the last slide I actually have with me, if I have the time, would be what I'm planning to do now. So I'm currently trying to upscale the modification of chitosan with a special regard on economically relevant parameters. So because I'm moving from academia to Fraunhofer, and Fraunhofer is more applied sciences, economical considerations are also very important. And then I would wish to, at some point, translate the experiences from the laboratory spinning setup to a multi-jet electrospinning apparatus, for example, from Elmarco. And then there's further investigation of the stable jetting modus done, not really so much from me, but it's done at Professor Menzel's working group with a focus on optical applications, as I presented a bit. And then what's also interesting for me and for us is a broader testing of other tagged enzymes and other biomolecules, and then in the end, the development of several products from that established platforms. And for this, we surely need some more interdisciplinary, international or national partners. And if you're interested, please contact us. So thank you again for your attention.
Thank you very much, Mr. Christ. And now it will be time for the questions. We will follow the same order as were the presentations. So we will start with the questions that are aiming Professor Ehrmann. And there is a few questions regarding the sterilization of the material. In the European Union, there is only few standard sterilization methods that are allowed. For example, it is like X-rays, it is ethylene oxide, it is autoclaving with steam. So did you try any of these standardized methods?
Yeah, autoclaving, well, of course, including steam, yes. That's, I would say that's one of the gold standards which we indeed use mostly. As I explained before, there we have the problem that some biopolymers simply won't survive this process. But as you saw, this doesn't really matter. So this may be still the best method. Ethylene oxide has, in our experience, the problem that normally if you do this with, I would say, flat surfaces, then you, okay, let's say put the sterilized stuff into lab food and wait for a week or two, and then everything will be fine. But if you do the same with the nanofiber mats, we always had the feeling that the nanofiber mats contained still so much of these traces of the ethylene oxide that we couldn't work with them with cells. So actually the cells were always dead. So we assume that just due to this very complicated structure of the nanofiber mats, it's not possible to use ethylene oxide since it simply cannot evaporate completely, and there will always be some residues, some traces of this, which are not good for the cell growth.
Okay, thank you. And so as I saw, the best method for sterilization was the UV light. Is it correct?
It really depends on the cell line. Actually, we mostly used the autoclaving because even in UV, okay, if you are just thinking about the structure of the surface, then UV would be a good point. But nevertheless, we always had better cell growth and proliferation and cell adhesion if we did some just simple autoclaving. And we also thought, because autoclaving sort of destroyed the surface, that it wouldn't be so good, but actually it was.
Mm-hmm.
Okay, thank you very much for the answer. Then there is another very general question for you. What should we pay attention when planting cells on nanofibers?
Okay, that's really quite general. one thing is, of course, sterilization. We had very often, and not only of the nanofiber mats, but also of the cell culture, we had very often problems that there were any contaminations, and sometimes this were simply contaminations coming from the really from the master batch of the cells. And but nevertheless, sometimes we just found that the sterilization process, for example, using this 60 degrees Celsius heat treatment, simply was not sufficient, and there was more or less always contaminations. So I would say this the sterilization stuff is quite important. And regarding combination of cells and materials, that's really tricky. We have on the one hand, depending on the cell which you use, some cells will prefer thicker nanofibers and some will prefer thinner ones. Very often cells will prefer nanofibers which are not growing chaotically, but which have a certain more or less defined orientation. So this is not what I've shown here, because this is more done in, as my colleague Mr. Christ showed, this is more done in the with a rotating collector, and so that's also something which we are doing, but not so often. The other thing is that even if you have some fibroblastic cells or fibroblast-like cells, which like these very long, elongated structures, even then, some of them will prefer, let's say, gelatin in addition to pan, and some of them will say, oh, let's grow on everything. So it really depends on the cells which you are using. And so I think it would be nice to have a sort of table where you can just put in your cells and can just check the right material. But until now, we just have we have 3 cell lines which we always use, and so we could only say for these 3 cell lines which materials would, in our experience, be the best, and maybe they are still much better. Maybe the pure chitosan is much better, but we didn't use this yet.
Okay, thank you. Then there is another question for you. If the cell growth after surface modifications were linear in time?
No, absolutely not. Normally, after a day or two, I would say even the maximum amount of cells is available. And so very often we used only 3 days or so for cell cultivation. This is really completely different from for example, we also worked with microalgae on nanofiber mats, and there you have an exponential growth until you reach the saturation. And this is completely different here for the cells. It really depends on the substrate, and very often you reach after a day or two the maximum amount of cells.
Maybe I have a question to Andrea. I made some notes during your first part of presentation that you mentioned that the best, actually, the treatment would be hot air treatment for sterilization, where, I mean, in terms of the cells growth, that giving you the best results. But on the other hand, the fibers, especially of fibers of gelatin, were destroyed by this method. So could you comment on that? So is it good for cells grow, but actually you don't have fibers anymore? It's maybe like a foil.
Yes. We didn't. If you have a pure gelatin nanofiber mat, it will be completely destroyed, and there will be no fibers at all anymore. And on this, we also tested this, and you really get a sort of foil. And we didn't find any cells which preferred growing on these gelatin foils. But if we have, for example, a combination of pan polyacrylonitrile with gelatin, then you have still a lot of fibers which are still there. So the base structure is still fibrous, and actually only these fibers which contain pure gelatin, they will be fully molten and they will be completely destroyed regarding the shape. So I assume that it's actually not so bad for the cells, that they have still a nice structure, and that they just have also the gelatin around, but they get the structure plus the material, but just in a different way. What we did once was we did electrospinning with pure pan and just dip coated it with gelatin. But this didn't bring exactly the same effect. We thought it would have the same result, but the cells were not so lucky with it. So maybe this little bit melting of the gelatin is the best for the cells.
Okay, thank you. We can
Okay,
continue.
thanks. So another question is regarding the polyacrylonitrile polymer itself. So did you use the homopolymer or a copolymer of polyacrylonitrile and any other monomer?
We have always copolymers. We are using Xpan from Dralon. It's just the one which the company is quite near to us, to our university, and luckily they often give us some of their polymer, and this was. We didn't see many differences. We tested some other pan polymers. But actually, for the cell, neither sometimes for electrospinning makes a little bit difference, but for the cell growth process, we didn't see differences whether we use this Xpan, which we normally use, or any other pan.
Okay, thank you. And you then carbonize this copolymer by normal techniques that are used for the creation of carbon fibers.
Yes, we have two ovens. One is a simple lab oven, which can go up to, let's say, 300 degrees Celsius. And the important thing is to use a very slow heating rate. So if we go up to normally to 280 degrees Celsius for the stabilization process in very small steps of normally 1 Kelvin per minute. And so in this way, this will be properly stabilized. And after an hour of stabilization at 280 degrees Celsius, we can take it out, and then we go into the furnace where we have an N2 nitrogen atmosphere, and there it's the nanofiber mats, the stabilized nanofiber mats are carbonized, and in this process, the ramp, the heating rate is not so important. It can be like 10 Kelvin per minute, and we also leave it there for around normally 1 hour. And depending on whether you whether you do the carbonization process at, let's say, around 500 degrees Celsius or 600 or 800 degrees Celsius, you will get different amounts of carbonization. And the higher the temperature, the higher is the carbon yield. But the more brittle these substrates will be. So the images which you saw before, these nanofiber mats have been carbonized only at 600 degrees Celsius. So it's not fully carbon.
Okay, thank you. And the last question for you at this moment: what was the substrate actually that you used to collect the polyacrylonitrile nanofibers?
Oh, that's the normal one from you. That's the normal PP, the blue substrate on the roll.
Okay,
it's the spun bond, yeah.
So it was the polypropylene spun bond.
PP, yeah.
Okay, thank you very much for the answers. There is actually no other questions here.
Okay. Thanks for your interest.
And we will move to your colleague. I mean, not to your colleague, but the second speaker, to Henrik. You mentioned that you use the chitosan from mushrooms, not from shrimps. Actually, how repeatable was the synthesis of this chitosan from mushrooms, and how repeatable are the products that you got from the company in Belgium?
So, it's a nice question. Thanks. Maybe let's answer the second part first. How repeatable are the products from the company in Belgium? So I can answer them partly because I got quite a big sample from university perspective and worked. Most of the experiments were done with only that batch, but nowadays I'm working again with the chitosan, and I would say it behaves quite normal. I did not redo every analysis again on the newer batches, but I would say this is quite a nice, a fine yellowish powder. There are not so many impurities that I could detect or see. And I'm quite fine with the standard. You have to mention that it's not medical grade chitosan. It's food grade chitosan that I've worked with, but it's very hard to get a lot of chitosan for a reasonable price in medical grade. And the second part of the question, how repeatable is the synthesis? That I had some issues in the beginning because the synthesis, I did not really talked about the pitfalls of the synthesis and the individual parameters that I've varied and checked. But you can read them, of course, in the publication. If you don't have maximal coupling efficiency, then the synthesis in the outcome of how the synthesis is a bit tricky, because if you say you would like to add 20% of aryl azide groups into the polymer, and you then have something of a coupling efficiency between 20 and 60, then that varies, of course, the final degree of substitution, and that again varies the electrospinning properties of the material. But if you have maximal coupling efficiency in the synthesis, then you don't waste any precious aryl azide or biotin functionalities. That's the first point. And the second point is you always get what you want. So you get the 20% that you desired and that you set in the beginning. And the main thing that you have to keep an eye on is the pH during the synthesis, because it's a pH sensitive method, and it basically sits in an optimum. And if you go a bit too high or a bit too low, then your coupling efficiency decreases significantly. But if you make everything correct, then I would say it's quite a nice synthesis.
So another question regarding this modification method is if you were not afraid to work with organic azides, because they are known to be explosive. So
I know they can explode, and we keep them refrigerated if we not use it. I did not had any explosions in the lab, and they are then dissolved in the solvent system, and later on removed via dialysis most of the time. So far we did not have any incidents.
Okay. Another question. You tried this chemical cross-linking after you modify the polymer. Did you try any other cross-linking methods of chitosan that will not require the chemical modification of the polymer itself?
Yeah, I've tested some. I've worked with glutaraldehyde, janepine, and also I would say basic, reversible cross-linking by just deprotonating chitosan, putting it into a bath of sodium hydroxide. But in no cases I was satisfied with how the fibers later on looked in the SEM. And that's why I set out to do the more laborious method of modification of the chitosan before spinning. But I know it can be done in sodium hydroxide.
Okay, thank you.
Yeah, maybe I have a question related to that, because you mentioned you use UV light for cross-linking, and I don't remember how long how long the UV light you need to apply. You were talking about seconds, but I'm not sure. But the question is, can you imagine that to be done like in a large scale when the chitosan is made in, let's say, in a speed of centimeters or even meters a minute, is coming from the machine, and then you would apply this UV light like online? Would you imagine to even shorten the time, or what? Are there any limitations in that?
I mean, I've not really explored all the boundaries in the photo cross-linking area. There is still a lot of research to be done to optimize it and to not use too much UV light, for example, because you can break, of course, your chitosan into fragments, or you waste some energy that you could otherwise use anywhere else. But I could imagine doing that, like in meters per second. Was that the speed?
Oh, per minute.
Meter per minute. I think that is doable. So in either you like just elongate the area of irradiation. That could maybe speed things up. Or you decrease the distance of the UV source and the irradiated thing to increase the energy. And as I showed, I did not show it today, but via the IR checking method, it's quite easy to see that even after 10 seconds of irradiation, most of the azides are gone.
Oh, okay.
And that could even be maybe used like during spinning. It's maybe a very interesting sterilization and cross-linking combination treatment.
Yeah, definitely. Thank you. Got more questions, right?
But there is more questions regarding this modification. For example, how you remove the reactants from the modified chitosan.
That is a big bottleneck, especially if you think about upscaling them, because it's if you want to be really sure and if you want to follow the gold standard, you have to use dialysis. From my perspective, you could dilute it out, but dialysis is also just that, putting it into a in between the membrane, the polymers, and dilute all the soluble products. That's why, for example, EDC is used, because it has a water-soluble end product. And yeah, so that's basically how you remove it.
And the last question at this moment, what do you use as a solvent for this modified chitosan? I guess it was in the presentation, but can you repeat it?
Yeah, so the same solvent as I use for the unmodified chitosan, it's 3% acetic acid in water, and 10% of the overall solvent system, 10 volume percent, is methanol. I've checked, of course, other organic solvents, and using no methanol at all. Spinning without methanol is a bit tricky, but I'm quite confident that it could be also get rid of methanol completely and just use diluted acetic acid.
Thank you very much. So that was our last question at this moment. Maybe we can forward the other questions that were not asked to the speakers.
Yeah, definitely. Then everybody has the opportunity also contact you either directly or through Elmarco if there are no questions or there are still questions remaining. So for this moment, we'd like to thank you for attention. And yeah, I hope to see you next time, like next month. And yeah, keep spinning.
Okay, thank you.
Thanks for the invitation.
Thanks for the invitation.
And see you in March.
Yep. Thank you. Thank you very much. Bye-bye.